Okay, so let's solve another problem. So this is see a conductor of active length 30 centimeters carries a current of 100 amperes. Okay, so there is a conductor and the length is 30 centimeters, or let me put it in meters, 0.3 meters, carrying a current of 100 amperes. Lies at right angles to the magnetic field of strength zero point 0.4 Webers per meter square. So let me draw the magnetic field. So let's say the magnetic field is perpendicularly down. Okay, so something like this. So magnetic field is in vertical direction and then the current is in horizontal direction. Calculate the force experienced in Newton exerted on it. So a current carrying conductor placed in a magnetic field. By the way, the magnetic field is zero point 0.4 Webers per meter square, or zero point 0.4 Tesla. So force experienced by a current carrying conductor placed in a magnetic field F is nothing but BIL. So Newton. So B is zero point 0.4 and the current it is carrying is 100 amperes, and the length is 0.3 meters. Okay. So this is zero point 0.4 Tesla. Okay. So zero point 0.4 into 100 into zero point 0.3. So this points will cancel out with zeros. So 4 into 3 is 12, and the answer is 12 newtons. So this is the answer for the first part. So this part is solved. If the now let me put that in the diagram. Okay. So the interesting question is the current is going from left to right, and the magnetic field is from top to bottom. In which direction is the force? Okay. So one direction I'll show A, and another direction I'll show is B. Okay. Is it A or B? Okay. So that is the question. So you can pause the video and then check your understanding whether it is A or B. I'm going to explain it very quickly here. And then later on you can match your answer. Okay? So you can pause it right now and then try to answer the question. Is the 12 newtons force which you calculated, is it in direction A or in direction B according to the diagram which I given? Okay, so what is the answer? So now if I want to know what is the force, what is the direction of the force, that means the output is mechanical. So therefore this is a motor. Therefore motor means you use the Fleming's left hand rule to determine the direction of the force. Okay, so you draw the left hand. So this is thumb, this is the first finger, this is the second finger, and then these are the other two fingers, and then this is the palm, and this is your left hand. So this is F, this is B, and this is I. So F is force, this is unknown, and B is flux, this is known, and I is current. Now try to align your left hand according to this figure. Okay. So the current is like this. So current has to rotate somewhat like this. Rotate, so you align this current like this because parallel to this 100 amperes current, and the flux is downwards. So keeping your middle finger pointing towards this direction, your flux finger should point downwards. So I'm trying to use my left hand here to do that. Okay, so I just checked it out. So if the flux is downwards, then the force will be at the other side. Okay, so the answer is A. Okay, so the correct answer is A, and the B is not the correct answer. Okay. So let me just summarize it. So if I go up, so a current carrying conductor carrying 100 amperes placed in a magnetic field which is coming downwards. So this is magnetic field. Will experience a force towards that side, Fa, and the force is 12 newtons of force. Okay, so let's go to the question. if the force causes the conductor to move at a velocity of 10 meters per second. See, this force is acting on the conductor, so as a result, conductor is moving at some velocity. So remember your Newton's laws that when a force is acting on a mass, the mass will start accelerating towards the direction of the force. And as a result, the velocity that is achieved by this current carrying conductor, velocity v, is nothing but 10 meters per second. Okay. So what? Now you have a moving conductor placed in a magnetic field. It will experience a force. So a moving conductor placed in a magnetic field will experience some force. Sorry, will an EMF is induced in it. Okay. So calculate the EMF induced in it. Okay. So already the mechanical input is there. It is moving at 10 meters per second and carrying. It is present in a magnetic field. It will experience some force. So sorry, I'm confusing you. So EMF induced is BLV. Okay. So B is flux density, that is already given zero point 0.4 Tesla. So that's here. So zero point 0.4. Active length is zero point 0.3 meters, and then velocity is 10 meters per second. So this is meters, this is in Tesla. So if you calculate this, you will get 1.2 volts. 4 into 3 is 12, and then 2 decimal points, but 1 decimal point we cut here, so it is 1.2 volts. So 1.2 volts of EMF is induced in this conductor. Okay. So that is the answer to the question. So again, what is the direction of this EMF? So just by applying a Lenz's law, so the direction of this EMF will be in this direction. So the positive will be this side and the negative will be this side. Just because the 100 amperes current is in this way, it has to be opposing that current. So the through Lenz's law I can tell that EMF induced will be in this direction. So the A will be positive as compared to B. So if I name these 2 points as A B. Of course, you can always, because this is EMF is generated, it's a generator, so you can use Fleming's right hand rule and you can draw all the right hand of the Fleming, and then you can always try determining what is the direction of the EMF. So here again force is that way, and then let me just quickly check now that I have drawn the figure. Flux is downwards. Yeah. So I can see that the EMF will be induced so as to push the current in this way. So my assumption is correct. Okay. So that's this. Let's continue. So EMF induced we have solved already. So the power in watts developed by it. Okay. So what is the power developed? So you see, there are two things like so mechanical power. So this is nothing but force into velocity and electrical power. So let me use a different color. This is what current into voltage. Okay. So what is the current? Current was 100 amperes. Already it was flowing in the conductor 100 amperes, and the EMF is 1.2. So into 1.2 volts. So this is nothing but 120 watts. Okay. So that much of electrical power is there. Okay. What about the mechanical power? So force into velocity. Okay. So force was 12 newtons. 12 newtons multiplied by 10 meters per second. So this is also 120 watts. 12 into 10 is 120 watts. So exactly again we are seeing mechanical power equal to electrical power. So for this example, which is the input and which is the output? Okay. So because it is given in the question that a conductor carries a current and lies at an angle to a magnetic field. So initial thing is it is carrying a current and therefore the force is being exerted on it. So the this is the input and this is the output. So basically what you are seeing here is a motor in this problem. But anyway, I think again this is yet another example. So I hope you have learned something about the
conversion between electrical and mechanical powers. All this entire conversion is because of the Faraday's laws that is there. So I hope you learned something from this, and I hope it is interesting. Let's continue.